previous lectures, we started from number 1, the principle of conservation of linear momentum, and what it said was that if I have many particles interacting with each other, as long as these interparticle forces obey Newton's third law, the net momentum, that is mi vi product summed over, is a constant if summation of external forces on each of the particles is 0. That is, if the net external force is 0, the total momentum of the system remains a constant. In other words, I can write d over dt of summation mi vi is equal to 0, and that is the principle of conservation of linear momentum. Related with this, when we considered momentum of many particles, was the concept of center of mass, which was defined. Suppose there are many particles at different positions. Let me call this one Ri, let the mass be Mi, then the center of mass coordinate R is equal to summation Mi Ri over summation Mi. The beauty of center of mass was or is that if I apply an external force, no matter how these particles are moving, they may be doing anything, the body may be deforming, the orientation may be changing, but the center of mass always moves as if the entire mass is sitting there and the net force F external is applied there, where m is the total mass of the system and F external is the net force, that is summation of F external I on each individual. In other words, if F external, the net external force is 0, I am going to have RCM dot is equal to constant. That is, the center of mass would keep on moving with constant velocity. We solved one example using this in the previous lectures. Third thing that we learned was the conservation of total mechanical energy, and what it said was, in a conservative field where the work done is independent of the path, the kinetic energy plus the potential energy of a system of particles is constant. In this lecture, we are going to look at these principles once again through examples to learn how we can use them effectively to learn about motion of these particles. As the first example, I am going to take two particles colliding with each other and going out. Let the particles be m1 and m2 masses. This is coming in with velocity v1. This is coming in with velocity v2. This is going out with velocity v1 prime, again m1, and m2 goes out with velocity v2 prime. I am going to assume that the interparticle forces act only in a very small region, so that before the collision and after the collision the particles are essentially free. The other thing I am going to assume is that this region is very, very small, and therefore during the interaction, when the particles go in, interact and come out, they hardly move. So PE, the potential energy, remains roughly the same, and therefore I can write by energy conservation that the Ke, or the kinetic energy coming in, which is 1/2 m1 v1 square plus 1/2 m2 v2 square, plus I'll add a term delta E to take care of energy which may be released during their interaction or which may be lost during interaction. So this must be equal to 1/2 m1 v1 prime square plus 1/2 m2 v2 prime square. That is what energy conservation gives me. If, or let me write the equation again and then we will talk about delta E. So the energy conservation gives me 1/2 m1 v1 square plus 1/2 m2 v2 square plus delta E is equal to 1/2 m1 v1 prime square plus 1/2 m2 v2 prime square. Now if delta E is greater than 0, that means the kinetic energy after interaction is going to be more than the kinetic energy that was coming in, and that means some energy has been released during the interaction. So this implies energy released during collision. This may be the case, for example, two particles colliding and some internal energy comes out. If delta E is less than 0, energy is lost during interaction, and this is usually the case which we call inelastic collisions. And third case may be that delta E is 0, and that is an elastic collision. So we have seen what the conservation of energy is going to give us. I remind you again that we have assumed the region of interaction is so small that the potential energy hardly changes, and the energy between the particles is essentially that of free particles, and therefore I am writing only the kinetic energy. The other principle is going to be the principle of conservation of linear momentum, and that tells me that summation mi vi is a constant if there is no external force. Since the interaction time is very small, we neglect any external force impulse that may be acting on the particles. So we assume that impulse due to F external is essentially 0, and therefore the only force that acts during that interaction time is that of the particles applying on each other, and therefore I am going to have m1 v1 plus m2 v2 is equal to m1 v1 prime plus m2 v2 prime. If there is external force, I can always take care of that by adding terms here, but for simplicity we are ignoring it right now and assuming that the interparticle force is really much larger than this. So we are taking the simplest possible scenario of two particle collisions and getting two conservation principles that tell us that the energy is conserved. Therefore this equation must hold: 1/2 m1 v1 prime square plus 1/2 m2 v2 prime square, and the other equation that should hold is m1 v1 plus m2 v2 is equal to m1 V1 prime plus M2 V2 prime. In case you have lost track of what's going on so far, let me remind you, two particles are coming in, interacting in a very short, for a short time in a very small region and going out. This particle has mass m1, this particle has mass m2, coming in with velocity v2, coming in with velocity v1, m1 goes out with v1 prime and m2 goes out with v2 prime. This is one equation, and for each component I can write one equation in this. So this is in effect equation number 2, equation number 3 and equation number 4. Therefore, I have 4 equations from which to extract information about the motion. The number of unknowns that I want to know after the interaction has taken place is v1 prime 3 components and v2 prime 3 components. Therefore, total number of unknowns that are involved in this are 6, whereas the number of equations that arise out of conservation principles are only 4. Therefore, using conservation principles, I cannot get the motion fully, or I cannot get all the 6 unknowns fully. For that, I really have to solve the equation of motion. However, now I am going to show you that these principles put constraints on motion and therefore are useful to tell us about what can happen, what may not happen. So let us look at an interesting case where two particles come in with velocity v1, m2 with velocity v2 get stuck together, so that out goes a particle of mass m1 plus m2 with some velocity v. Then the energy conservation principle tells me that 1/2 m1 v1 square plus 1/2 m2 v2 square plus delta E, which is the energy released or lost during this interaction, must be equal to 1/2 m1 plus m2 v square. And the momentum conservation tells me that m1 v1 plus m2 v2 must be equal to m1 plus m2 v. Let us see, by using these two conservation principles, what can I learn about the motion or the restrictions on the motion. From this equation I am going to substitute here. Before that, let me cancel this 1/2, 1/2, 1/2, put a 2 here, and now substituting this v here, I get m1 v1 square plus m2 v2 square plus 2 delta E is equal to m1 plus m2, and I substitute for v, which is m1 v1 plus m2 v2 with vectors here, square divided by m1 plus m2 square, which is equal to, I can take away this power, and therefore I get m1 plus m2 m1 v1 square plus m2 v2 square plus 2 delta E is equal to m1 v1 square plus m2 square v2 square plus 2 m1 m2 v1 dot v2. In case you have gotten lost, let me remind you what I did. I wrote the energy conservation principle, I wrote the linear momentum conservation principle, and from the linear momentum conservation principle I substituted for the final velocity in the energy conservation principle, and I am just rearranging the terms. Collecting them, I am going to get m1 square v1 square plus m1 m2 v2 square plus 2 delta E m1 plus m2 plus m1 m2 v1 square plus m2 square v2 square is equal to m1 square v1 square plus m2 square v2 square plus 2 m1 m2 v1 dot v2. This fellow cancels with this fellow cancels with this, and I get, rearranging terms, I will take it to the left hand side. I will get m1 m2 v1 square plus v2 square minus 2 v1 dot v2 is equal to minus 2 delta E m1 plus m2, or I can write this as v1 minus v2 square and therefore get v1 minus v2 square is equal to minus 2 delta E m1 plus m2 over m1 m2. This is a very important result, and now we are going to see what all it teaches us about the motion. Let me write this again on the next slide. What I have obtained by combining the two conservation principles, v2 minus v1 or v1 minus v2 square is equal to minus 2 delta E m1 plus m2 over m1 m2. Notice that the left hand side is a perfect square, so it is always greater than 0. On the other hand, right hand side, so this is the left hand side, the right hand side could be greater than 0, 0 or less than 0 depending on the sign of delta E. If delta E is greater than 0, then the right hand side is less than 0, and therefore the left hand side and the right hand side can never be equal if this condition is satisfied. What does this mean? Recall again, what are we doing? Two particles coming in, interacting and going out as one particle, m2, m1, m1 plus m2. If during the interaction some energy is released, that means delta E is greater than 0, I can never satisfy this equation and this interaction will never take place. So, if two particles during interaction release energy, they will never get stuck together and go out as one particle. For example, if two atoms collide and make a molecule, they will never do it in free space if during their formation of that molecule some energy is released. On the other hand, if delta E is less than 0, then right hand side is greater than 0. That means during the interaction some energy is released, some energy is lost, and that is an inelastic collision, and this does take place as you have seen in your 11th and 12th grade also. Third case, if delta E is equal to 0, that interaction is also not possible because the right hand side is 0 and the left hand side is greater than 0. So, this is an elastic collision. In an elastic collision, two particles will never really get stuck together. Through the example that we just solved, we saw how the combination of two conservation principles tells me whether a particular reaction or a particular collision is allowed or whether it can take place or not.